So, for the sequel of this morning, it's my great pleasure and honor to introduce Professor Curtis McMullen from Harvard University. Professor McMullen has won the most prestigious awards. He is well known for his beautiful works in knots, complex dynamics, Riemann surfaces, and hyperbolic three manifolds, and many other fascinating subjects. His talk today will be on the evolution of geometric structures on three manifolds. Professor McMullen.
Thank you. Well, it's a real honor to be able to participate in this celebration of the proof of the Poincare conjecture and of Perelman's brilliant work. Perelman and I were colleagues at Berkeley in the 1990s. I remember especially a very lucid description he gave at a Miller lunch to a group of biochemists and engineers of his work on Alexandrov spaces, which would later form part of the endgame in the proof of the Poincare conjecture. And it was clear already then that he was someone who was immune to conventional lines of thought. And so when I heard in the early days of 2002, 2003 that an apparently correct proof of the Poincare conjecture was circulating on the internet, I was as surprised as anyone else, but I wasn't surprised when I learned the author was Perelman. So my goal today is to give a very impressionistic account, not so much of the Poincare conjecture, but of the geometrization conjecture. The geometrization conjecture is a vast and ambitious program described first by Thurston, which aims not just to describe how to characterize the three-dimensional sphere, but to give a complete account of three-dimensional geometry and topology. And I really would like to convey the full gravity of what Perelman has achieved by giving you a glimpse of what this geometrization conjecture says. That is my goal today. So let's start with the geometrization conjecture in dimension 2. So, as has been mentioned many times, and I think is eminently plausible, although it took some time for people to even formulate a precise statement, let alone a proof of this theorem, it's easy to classify surfaces. Closed orientable surfaces are classified by the number of handles they have, and this is called the genus. Well, let's accept that as a topological classification of two-dimensional manifolds. But this classification can be made much more elementary. That is, you can give very simple, specific geometric examples of two manifolds of each genus. One of the simplest is to give a geometric example of the torus. So this is supposed to be a top view of a torus here, and you can build a torus out of Euclidean squares. How do you do it? Well, you start with this flat piece of the plane, you wrap it up to form a cylinder, and then you bend the ends around to make the tube close up and form a torus. And what you see is that, think of this picture as only being topological. The shape of the squares are distorted, but they fit together beautifully at the vertices because they have 90-degree angles. So in this picture, there are 8 squares which are neatly tiling a surface of genus 1, a torus. There's 4 on the top, and there's 4 on the bottom. So a surface of genus 1 can be geometrized. It can be described neatly using tiles from Euclidean geometry. Well, in the same way, a surface of genus 2 can be neatly tiled, this time not by squares, but by pentagons. So here's a picture, a top view of a surface of genus 2, and it's been cut into 4 pentagons. There's 4 pentagons on the bottom. Well, by pentagon, I mean that this rather distorted shape here has 5 sides. Now, you see that 4 pentagons come together at a vertex, so if we just had a big supply of right-angled pentagons, we could easily build a surface of genus 2. I would bring one in to show you. But those don't exist in Euclidean geometry. However, that's just a psychological barrier. This kind of beautiful geometric regular polygon exists in hyperbolic geometry. So this is a model for the hyperbolic plane. It's a substitute for the Euclidean plane. It has a boundary at infinity here. And in hyperbolic geometry, there exist regular pentagons with lots of different internal angles. And in particular, there exists a unique regular pentagon with a 90-degree angle at every vertex. So if you have a supply of these hyperbolic tiles, then you can use 8 of them to build a surface of genus 2. And if you have more, you can build a surface of genus 3, or of any genus greater than or equal to 2. So this insight is what we might call the geometrization theorem in 2 dimensions. It says that these surfaces of various genera, genus 0, genus 1, and genus 2, can all be built out of geometric pieces. For example, the sphere already carries a natural geometry. It can be tiled also by pentagons, but spherical pentagons this time, which have a little more angle than they would have in the Euclidean case. They're sort of overinflated, as opposed to these underinflated polygons that arise in hyperbolic geometry. Anyway, this idea that you can build all surfaces geometrically was already realized by Klein in the 1870s, although I think it took some time to reach a modern formulation. Manifolds were generally thought of as concrete objects in these days, and this was just another concrete way to make surfaces of arbitrary genus. Now, in last night's beautiful talk, Gis described some of Poincaré's contributions to the theory of surfaces at the turn of the century, or more precisely around 1881. Let me just mention the difference between what he was doing and what the geometrization conjecture says. The geometrization conjecture for surfaces, this fact that you can build all these surfaces out of these simple geometric shapes, is extremely elementary. It's something that high school students can easily understand once they've surmounted the psychological barrier of working in spaces of positive or negative curvature. The concern in the late 1800s, however, was with a more analytic statement of the following type, called the uniformization theorem. You have one very concrete type of surface, say the 0 set in the complex numbers of an algebraic relation between 2 variables. Perhaps the global geometry of the solutions to this equation in C2 is essentially a surface of genus 2. Now, there's another way to make surfaces geometrically in terms of these tilings. And what one would like to know is that there is an analytic map from the unit disk onto this algebraic object, which wraps up these tiles and neatly fills out this given algebraic solutions by these geometric tiles. And it's the construction of that analytic map that is, whose existence is posited by the uniformization theorem, and which was one of the objects that Poincaré tried to analyze and construct. Now, what I want to point out is that in those days, it was clear that you could take a picture of the hyperbolic plane, you could take an action of a group on it by isometries, preserving some tiling, and get a surface like this. But what was not at all clear was that even if the surface was presented to you in this way, that the surface was given by an algebraic equation. To prove that this quotient is given by an algebraic equation is tantamount to constructing functions on the disk that are invariant under the action of the group, especially algebraic functions that would play the role of y and x in this model for the Riemann surface. So a big problem was to construct functions on the disk, so-called Fuchsian functions, or theta quasi-Fuchsian functions, as Poincaré called them, that are invariant under the action of this group. Now, how can you construct a function on the disk that's invariant under the action of some infinite group? Well, it's easy. You just take any function that you like, and then you start moving it around by the action of the group, and you sum, and then the result is invariant. Now, the sum is unfortunately infinite. That wasn't such a big deal in those days, but it really converges very badly if this function is just an ordinary, say, analytic function on the disk. And the reason is that there's thousands of tiles near the boundary here, and you're adding up the value over all of those tiles. Unless the function vanishes identically on the circle, there's no way this sum is going to converge. And one of Poincaré's brilliant insights was that this sum here converges without difficulty so long as you replace this function by a form. That is, if you think of this f as representing a holomorphic quadratic differential, then it turns out that this sum converges, and it converges basically because the area of the disk is finite. And so what Poincare did was, instead of constructing meromorphic functions directly, he constructed these invariant holomorphic or meromorphic forms, and then ratios of them gave algebraic functions on the quotient surface. Okay, so much for two manifolds. Now, in the case of topology in genus 2, we had a very simple account of what the surfaces are. They fall into a natural order, genus 0, 1, 2, 3. They're indexed by the integers, and almost all of them are hyperbolic. That is, they are covered by the unit disk. What happens in dimension 3? So this is what the world of three-dimensional manifolds looks like at first sight. First, it doesn't have anything like a linear ordering. At best, it has a sort of tree-like structure, reminiscent of the evolutionary tree. But it's just daunting to try to find some order in this world. Nevertheless, Thurston proposed and Perelman proved the following geometrization conjecture. And it's very closely analogous to the two-dimensional case I just mentioned. The conjecture is that all three manifolds can be built using just 8 types of geometry. And this is Perelman's achievement, and it's to complete this program. And the stunning aspect of this achievement is that it gives then, in some implicit way, a description of all three-dimensional manifolds. The description, in other words, it describes this world here. But this world is not simply ordered in any way, but the beautiful fact is that when you find sort of the flesh of a geometric manifold, like you might unearth the bones of a dinosaur, you can reconstruct its original pristine geometric shape, and in fact this can even be done in practical terms by algorithms that run on computers these days. Okay, so let me briefly say something about these 8 geometries. Why are there 8 instead of 3? So there are 3 geometries of constant curvature. Spherical is positively curved, Euclidean is flat, and hyperbolic geometry, which will play the central role in the discussion, and which will account for almost all 3 manifolds, is of constant negative curvature. Then there are some manifolds that I would say, they appear to be three-dimensional, but they're actually dimension 2.5. Example, you take a surface of genus G and you cross it with a circle. Well, it's now three-dimensional, but it's not very three-dimensional. And more generally, you can take a twisted product of a circle over a surface, a circle bundle over a surface, and its geometry is not terribly rich. However, it does not admit, in general, one of these geometries of constant curvature. And so there's 6 other geometries which are necessary to handle all of these manifolds of dimension 2.5. And there's another way to make a 2.5-dimensional manifold, which is to take a torus bundle over the circle and twist it slightly. And there's 3 ways to twist it, and there's 3 geometries that account for each of those types of twists. And you'll notice that not all of these geometries are distinct. Nil is both here and here, and that's because some manifolds can be presented in 2 different ways. So the upshot is that to have a complete account of the theory of 3 manifolds, you need all 8 geometries. But to have an impressionistic account, you just need hyperbolic geometry. And my goal in this talk is to give a completely impressionistic account of what the geometrization conjecture says. So we'll come close to grossly simplifying it and focusing mostly on these hyperbolic 3 manifolds. Okay, so these others are to handle twisted products. So let me start with, in some ways, the simplest 3 manifold, which has, of course, played a prominent role in John Morgan's talk, is the subject of the Poincare conjecture, which is called the 3-dimensional sphere. Now, the 3-dimensional sphere, as a topological space, was already known in the 1300s. It occurs in Dante's conception of the union of our mortal world, the Earth, plus the concentric circles of hell, nesting down to the center of the Earth, plus the concentric circles of heaven, which mirror the concentric circles of hell and which also nest down to a single point. So Dante's cosmology had this form. There's the Earth and the hellish circles down here, and then there's the celestial sphere, and then there's various spheres with angels, and then finally there's this sort of north pole of the universe called the Empyrean, where the deity resides, and the entire shape is a closed object which is topologically the three-dimensional sphere. So this is what I want to say about the three-dimensional sphere, is that the concept of this topological space, that our entire universe might be closed rather than just open universe of endless space, was already something that was accessible to the imagination in the 1300s. However, what Dante did not realize is that this three-dimensional sphere can be made geometric. That is, this world can be made perfectly round in the same way that the two-dimensional sphere can be perfectly round. And once it's round, it has an enormous amount of symmetry. So, for example, you can take the mortal world that we live in, the surface of the Earth, and you can rotate the universe so that part of it passes through heaven and part of it passes through hell. And the geometry of the surface in no way distinguishes, the geometry of our universe in no way distinguishes between the celestial sphere and those two special points. Okay, so let's go on to another geometric manifold, namely Poincaré's fake sphere, which was also mentioned in the previous talks. So Poincaré constructed an example of a manifold which is not the three-sphere, but which admits a metric of positive curvature and which has no homological holes in it. And you can now, these days, we can visualize what his manifold looked like, and it's kind of a natural successor to the tiling of the sphere by 12 pentagons. So what is being rendered in this computer graphic is a tiling of the three-dimensional sphere by 120 dodecahedra. So there's a 12-faceted object here, which is a spherical dodecahedron. You can see its pentagonal faces rather clearly. And this is just a puffed out version of the traditional Euclidean dodecahedron. And because it's puffed out, the angles are just right so that you can fit several of these together around an edge and form a tiling of the three-dimensional sphere. By the way, there's one dodecahedron missing in the picture, which is the one that covers the pointed infinity in this, as well as this room. And all the rest form a finite part of the sphere. And this tiling admits a group of symmetries of order 120. And the quotient is another three-dimensional manifold, which admits a metric of constant positive curvature. And of course, historically, the importance of this was that that manifold has trivial homology. But you can tell it's not a sphere by looking at its fundamental group, which is just this group G. Okay, finally, let's let some air out of the picture. So if you take these dodecahedra, or one of them, and you deflate it, so it goes past Euclidean and becomes slightly bowed inward, you get a dodecahedron that can be realized inside the hyperbolic 3-ball. Now, the hyperbolic 3-ball has infinite volume. Unlike the sphere, it's not compact, so it takes infinitely many tiles to fill this three-dimensional hyperbolic space. And one thing that I find beautiful about this picture is if you look at the corners of this dodecahedron, well, you just see ordinary Euclidean architecture. It looks like you could actually build this at home. It's just that by the time you got around these 5 beams, you would be in trouble. And one of the special features of three-dimensional geometry, especially hyperbolic geometry, is that you need a very precise plan if you want to build this object. The length of this beam is uniquely determined by the fact that it forms one of the edges of a right-angled pentagon. The entire structure is completely rigid. It's a miracle that it exists at all. And this is one of the reasons why Thurston's conjecture is so striking. I mean, by the 1930s, when a variant of this manifold was discovered by Seifert and Weber, there were only a handful of examples of hyperbolic manifolds. And they were all extremely intricate and sort of rigid and could barely, they were like jewels that had fallen off of a crown. How could these possibly be avatars of a general three-dimensional manifold? Okay, so let me say a little bit about the impact of the geometrization conjecture. So I'd like to compare the Poincaré conjecture, which says that the only simply connected three-manifold is the three-sphere, to Fermat's last theorem, which says that the only solutions to some other equation are trivial. I mean, they both say the only solutions to some equation are trivial. Both theorems have stimulated a tremendous amount of mathematics. Both theorems are extremely difficult to attack ab ovo. Why? Because they say something doesn't exist. And you can spend a lot of time convincing yourself that something doesn't exist, and then you find a flaw in your argument, and so maybe it does exist. So how did the geometrization conjecture affect mathematical progress? Well, the geometrization conjecture implies the Poincare conjecture because the only simply connected geometric manifold would have to have a compact universal cover, and the only available universal cover is the three-sphere. On the other hand, any three-manifold provides a test for the geometrization conjecture. The geometrization conjecture says that a typical three-manifold should be built from geometric pieces, and in fact, the typical case will not be spherical but hyperbolic. And this is something that we can try on the countless three-manifolds that are known to exist, rather than pondering the fake three-sphere, which we're hoping doesn't exist in the first place. And in much the same way, the modularity conjecture of Shimura, Taniyama, and Bay is a positive statement that implied the solution to Fermat's last theorem. And indeed, the analogy goes farther. The modularity conjecture is a hyperbolization statement. It says that every elliptic curve defined over Q is dominated by a modular curve. What does that mean? It's a Riemann surface of the form, the quotient of the hyperbolic plane, by a congruent subgroup of SL2Z. And again, this positive statement, or the reformulation of the problem in terms of a much stronger positive statement, was an essential step leading to the progress by Wiles and Taylor and others, and the finally establishing of this much more central modularity conjecture. And what Perelman has achieved is, again, the establishment of not just the Poincare conjecture, but this vast geometrization conjecture regarding all three-dimensional manifolds. Now, what else can I say about the impact of the conjecture? So before the modularity conjecture was proved, it was investigated experimentally. So here's a catalog of something number theorists are fond of doing. They enumerate elliptic curves according to conductor. They try to match them up with modular curves, and they were successful. There's a big table of data that was produced by Cremona in around 1992 that gave abundant evidence for the modularity conjecture. What was the impact of the geometrization conjecture? Well, let me give you a brief tour of knot theory prior to the geometrization conjecture. So a knot is some sort of twisted up tube sitting in the three-dimensional space. You regard two knots as being the same if you can bend and twist one until it achieves the form of the other. If there's no way to untie the knot, then it's not the unknot, and one can try to classify knots. Now, this classification was instigated by Lord Kelvin, who proposed that atoms were knotted vortices of ether, and that the different knot types would account for the different elements. So perhaps hydrogen is the unknot, and helium is the trefoil knot, so on, lithium, carbon, mercury. And motivated by Kelvin's proposal, Tate and Little undertook an enumeration of knots. So they enumerated all of the knots up to 10 crossings. Here's a small part of the table. There's 249 knots altogether. And I mean, imagine how difficult this is. For example, this knot should appear somewhere in this table. Can you see where it is? I mean, it might be in a slightly different twisted around form. So, and one of the things that's very challenging is to tell when you've accidentally written down the same knot twice. Now, I should say that although this undertaking took 10 years, that was at the turn of the century, in fact, in the time of Poincare, that in the 1960s, John Conway, the combinatorial mastermind, developed a new notation for knots and was able, by hand, in a much shorter amount of time, to not only replicate the Tate and Little table, but to extend the enumeration to 11 crossings. Both tables were wrong. So there's a famous pair of knots called the Perko pair, which look different, but are in fact equivalent to one another, as was discovered in 1974 by an amateur mathematician, in fact a lawyer in New York by the name of Perko. So you see the kind of challenges that one is faced with this most elementary of three-dimensional questions, the enumeration of knots. Well, now let me say a word about the geometrization conjecture apropos knot theory. You see, the geometrization conjecture applies not just to closed manifolds, but also to manifolds with torus boundary. So the complement of this knot in the three-sphere should also admit a hyperbolic structure, not one of compact type, but one at least with a complete metric of finite volume. And if you can find that hyperbolic structure, if you can determine how to build the complement of this knot out of a couple of tetrahedra in hyperbolic space, if you can find a sort of analog of that dodecahedron I was showing you earlier, then you can extract all sorts of information that serve as invariants of the knot. Why? Because that geometric structure is completely rigid, just as it was for the picture of the dodecahedron. That's a result called Mostow rigidity that says that the topology determines the geometry in dimension 3. Now, one does not have to prove the geometrization conjecture to use this insight. If you believe there's going to be a hyperbolic structure, you can search for it. And if you find it, then you can use the invariants which result to classify knots. And using this idea in a little Macintosh computer, in the late 1900s, Host, Thistlethwaite, and Weeks enumerated the first 1,701,936 knots. And in fact, they really did it. I mean, they worked in two independent groups and they got the same answer. And this enumeration of all knots up to 16 crossings was made possible by the insight that hyperbolic geometry provides a sort of infinitely rich set of invariants that can be exploited to tell when you really have two different knots. And not only that, but this procedure, when you feed it the Perko pair, it first says, these two manifolds seem to have the same hyperbolic volume, then they seem to have some other invariants, and then it builds a complete combinatorial invariant of the manifold, and it proves that these two knots are the same. Using, I should say, a result of Gordon and Lukey that says if the knot complements are the same, then the knots themselves are the same. Okay, so that's a remarkable development in which three-dimensional topology has become sort of algorithmically tractable through geometry. Let me mention a couple of other famous examples of hyperbolic knots. The complement of the figure 8 knot is a quotient of hyperbolic space by a group which is more or less the 2x2 matrices with entries in the Eisenstein integers, Z adjoin a cube root of unity. And the Whitehead link, which is the complement, this is a two-component link, not just one knot, but with two loops, is essentially the quotient of hyperbolic space by the action of another discrete group. The reason that these other knots were not found or not recognized as hyperbolic manifolds, and in fact that it seemed very unreasonable to imagine that they could possibly be, is that the groups which uniformize their complement, the groups that give them their geometry, are not nearly so simple to write down. They are not arithmetic subgroups of the group of 2x2 complex matrices, which, by the way, is the same as the isometries of hyperbolic 3 space. So the groups themselves do not have nearly so simple descriptions, but nevertheless, they're totally unique, and associated to each knot is a certain number field and all sorts of rich and rigid geometry. Now, as I mentioned a moment ago, the prime invariant of a three-manifold that emerges from this perspective is its hyperbolic volume. Let me just give you an example. The volume of the complement of the figure 8 knot, this is the simplest hyperbolic knot, is given in terms of this Lobachevsky function by, in fact, a simple integral, but the result of that integral is presumably a transcendental number. So somehow this very simple combinatorial topology canonically determines this transcendental number. And you can compute this number for other knots. If it doesn't come out to be the same to 10 digits, then they're not the same knot. Okay, now a word about Thurston's breakthroughs in the 1980s. So again, this is impressionistic. Every expert will realize there are white lies. So Thurston showed that almost all knot complements are hyperbolic. So in other words, the geometrization conjecture, he explained why these computer programs are successful. In fact, a randomly chosen knot will have a hyperbolic complement. It will have a rigid geometry. Even more remarkably, he showed that almost all surgeries of the three spheres along knots and links yield hyperbolic manifolds. So what is a surgery? This means you take a torus inside of the three sphere, a solid torus, you remove it, and then you glue it back in differently. It's a simple change in the topology of the manifold. Now, the original torus might be knotted. And what Thurston showed is that for almost all knots and links and almost all choices of these surgeries, you get hyperbolic manifolds, as posited by the geometrization conjecture. Why is that such a great result? It was already known that all orientable three manifolds can be obtained by surgery on the three sphere. So this showed already that almost all three manifolds satisfy the geometrization conjecture. And finally, the engine that makes this all work is a theorem that says that if you glue together two hyperbolic three manifolds with boundary, that the result will be hyperbolic unless a small accident occurs, namely that there's a two torus incompressibly embedded in the resulting closed manifold. So let me just give a hint of how this beautiful theorem, the engine of Thurston's theorem, works. So we're now working not with closed three manifolds which are rigid, but with open three manifolds, manifolds with boundary. It turns out the boundary has the natural structure of a Riemann surface. And now we have a map identifying these two boundary components, and we want to show that when we glue this piece to this piece, the result is hyperbolic. But these pieces do not have a canonical geometry, and what we really want to do is deform them so that they match perfectly, and so that when they glue, the geometry pieces together seamlessly across the boundary. And then the theorem is that that works unless the fundamental group of the quotient contains a copy of Z2. That's your torus. Okay, now one of Thurston's great insights was to reformulate this gluing problem as a fixed point problem. And what he showed is that there's a natural map from the Teichmüller space of the boundary of M, that is the space of possible complex structures on the boundary, to itself. And if this map has a fixed point, then that fixed point will provide the desired hyperbolic structure. So the core of the geometrization theorem is to prove the existence of this fixed point. And I want to give just a hint of the proof, and I'm going to give a hint of an analytic proof. Okay, why? Because it relates back to what Poincare did with great foresight already in 1881. Namely, it turns out that, well, if you want to show a map has a fixed point, it's always good to try to show it's contracting. If it's a strictly contracting map on a complete metric space, it has a fixed point, and your work is over. Well, what one can show, this is a technique I developed in the 1980s, is that at a given point in Teichmüller space, the amount of contraction of this first mapping here is bounded by the norm of Poincaré's theta operator, this operator that takes a function on the unit disk and uses it to produce a function on the quotient that builds automorphic forms. And moreover, the norm of this theta operator is strictly less than 1. This was an old conjecture due to Erwin Krah, and it's, the idea of applying it in this setting was due to Doherty and Hubbard. And once you have this contraction, you're fairly confident that you're going to find a fixed point. Notice, however, I didn't say less than a constant strictly less than 1. You don't quite get uniform contraction, but if you don't get uniform contraction, then you go off to infinity in the space of Riemann surfaces. When that happens, some curves get short on the boundary. Those curves turn out to bound cylinders inside the pieces. Those cylinders piece together to give a torus, and that torus provides an obstruction to making the glued up manifold hyperbolic. So there's a quick proof of Thurston's approach to putting geometric structures on three manifolds. Notice that the approach is sort of bottom up. You start with hyperbolic structures on pieces. You try to put hyperbolic structures on the results of gluing them together. And it is an evolutionary process in the sense that you can start with a random geometry on these two boundaries, and then you iterate this map to improve it, sort of like Newton's method, to try to get closer and closer to the desired fixed point. Okay, so in the few minutes remaining, let me relate this to evolution by curvature. So this is the technique that was introduced by Hamilton and that was used by Perelman in his remarkable proof of the geometrization conjecture. So the proof is based on the Richie curvature flow. So what does this mean? Well, there will be many other talks which describe the technical engine of Perelman's proof. Let me just say a word about the equation. So what he posits is we start with an arbitrary metric on our manifold, and then we let it evolve in time, hoping to get a better metric, perhaps getting a hyperbolic metric, or maybe even a spherical metric if we started with a 3-sphere. And how do we change the metric in time? Well, we change it by a multiple of the Richie curvature, which Michael Attia alluded to in the first talk. Now, I have to say this, I was struck by hearing a description of this equation in a talk on evolution at Harvard. And I found this quote by Stephen Jay Gould, the famous evolutionary biologist, recently deceased. He said, Darwin recognized that his weakened negative force, notice the minus sign here, could only play a creative role if variation met 3 crucial requirements: copious in extent, meaning it takes place at every point on the manifold; small in range of departure from the mean, well, that means that it's a differential equation; and isotropic. Isotropic means it doesn't favor any direction, so the evolution must be guided by a tensor which is natural. And the only natural tensor that's of the same type as the metric is the Richie tensor. And so the process of course, Gould is speaking about natural selection, and yet the same sort of principles seem to guide this, the selection of this evolution by curvature. Now, this is the most impressionistic part of the talk. I would love to show you what it actually looks like when you apply this differential equation to a metric on a manifold. So the main thing to realize is that all the points on the manifold are moving as independent agents. They're not talking to one another. And nevertheless, somehow the topological form of the manifold begins to emerge, and then that topological form begins to straighten out and assume a geometric form. And so these independent agents, acting sort of by the unseen hand of Adam Smith, cooperate to solve the geometrization problem. Now there's a major difficulty, which is that singularities can develop in the manifold as this process takes place. But what Perelman showed is that, in fact, those singularities are a good thing. Sometimes you might have a hyperbolic manifold and another type of manifold, say a Euclidean manifold, and you might have taken their connected sum. Well, then you have to first cut them apart before you can put a geometry on them. And what Perelman showed is that, in fact, the singularities always undo these kind of connected sums for you. So, in fact, they're a good thing. And once you've decided you're going to do some surgery to eliminate these singularities, then the evolution continues for all time. And then eventually, the underlying architecture, that is the geometry of the manifold, becomes visible. And consequently, the geometrization conjecture is true, and consequently, the Poincare conjecture is true. Okay, here's a quick sort of naive connection with a physical question. As a consequence of the geometrization conjecture, general relativity places no constraints on the topology of the universe. Now, how can I make those words seem true? So, of course, there's a lot of assumptions. So general relativity also involves the Richie tensor, but what it says is that if we assume that matter is distributed evenly in space, then the metric on our universe, or on a space-like slice of it, should be a metric of constant curvature. Now, it might be of positive curvature in some manifolds, it might be of zero curvature, or it might be of constant negative curvature. That's also admitted in some models. Well, if we admit that our universe might have constant negative curvature, then the topological possibilities are endless, because almost all 3 manifolds arise as manifolds of constant negative curvature. So we can't tell by pure thought what the shape is of our universe. In fact, there's way too many possibilities. Okay, so let me conclude by saying just a few words about the comparison between these results, these methods of Thurston and of Perelman. So the Thurston's method is very classical and geometric. It uses the idea of tiles. It uses geometry of constant curvature. It can be implemented by computer algorithms. Perelman's approach uses smooth metrics. It uses infinite dimensional spaces, and it uses variable curvature. It's much more in the spirit of Riemannian geometry and heat flow. Thurston's method is bottom-up. It uses a hierarchy where your manifold is cut into pieces and then reassembled. Perelman's method is top-down. You start with a metric on the whole manifold, and if necessary, the manifold will break into pieces to reconstruct its geometry. And one very striking difference I want to draw attention to is that this fixed point problem that's solved in Thurston's method, it's the fixed point for a contracting map. So we know that the fixed point is unique if it exists. That's a manifestation of Mostow rigidity. In some sense, the approach on this side leverages Mostow rigidity to the fullest. Perelman's method does not even prove Mostow rigidity. It doesn't show that the hyperbolic metric is unique, it just finds one. And the main feature is not one of contraction, but of monotonicity. One of the main things he needs to rule out is that as you apply this Richie flow, you don't come back to where you started. Because if you come back to where you started, you're never going to get to the end. And finally, why was Perelman's method successful in handling general manifolds, whereas the bottom-up method was not yet, and it still may be? Well, there's some serious difficulties in handling the general case because a general three-manifold may have no surface along which to cut. So you can't start your inductive proof of the existence of a hyperbolic structure. And this is related to the fact that if you have a knot, well, then the strands of the knot can undergo elementary moves when they pass through each other. And to analyze a general three-manifold, you might first cut out a knot and then try to make it the complement hyperbolic and then analyze what happens as you put a cone metric along this knot. But these crossings are really problematic. Okay, now what happens in Perelman's method? Perelman's method is like a heat equation. If you start with a metric that's singular on a knot, it immediately becomes smooth. And so these strands here, which have to cross each other in a complicated combinatorial way from the geometric point of view, become diffuse tubes of strong negative curvature in the metric, and they can easily smoothly pass through one another. And so Perelman's method welcomes singularities in two senses. First, a singular metric is immediately smooth, and secondly, the singularities that develop actually leverage the proof. They give the connect sum decomposition. Okay, well, there's some other things to say, but in view of time, let me finish with just two statements. The first is the statement that there are now methods to take the Jones polynomial, that is this quantum discussion that Michael Atiyah alluded to, and leverage that to compute the hyperbolic volume of a knot complement. And this is really incredible for the following reason. It's not just that the Jones polynomial people haven't been talking to the Thurston and Perelman people. It's that the elements of the Jones polynomial discussion are basically quantum in nature, whereas the elements of the geometric discussion are, well, they're geometric in nature. They're sort of more like general relativity than like quantum fields. Nevertheless, a suitable limit of these quantum computations reveals the fundamental hyperbolic invariant, which is the volume. So this is only verified in a couple of cases, but it hints that within mathematics itself, there is a metaphorical echo of the fundamental problem in physics, which is to unify gravity and quantum field theory. Here we have a sort of quantum kind of mathematics that we would like to unify with the geometric kind, and that certainly remains as a challenge. So in conclusion, let me just give you a quote from the English mathematician Hardy. This appears in Littlewood's Miscellany. C.B. Snow author of the Narnia Chronicles, once remarked to the English mathematician Hardy that mathematical fame is a little too anonymous to be wholly satisfying. Hardy later wrote, "If I had a statue on a column in London, would I prefer the column to be so high that the statue was invisible, or low enough for the features to be recognizable? I would choose the first alternative, and perhaps so would Perlman."